In this video, we're going to talk about extraction. By the end of this video, you should be able to explain the basic principles of extraction as a separation method in a chemistry lab, apply extraction principles to separate a mixture of compounds in a chemical reaction. So, what is extraction? Extraction is a common separation technique used in chemistry experiments where a solid or liquid is transferred or extracted from one phase or solvent to another phase or solvent. Why is extraction useful? Chemical reactions are not 100% efficient, so in addition to the product, there is usually some unreacted starting materials or products from side reactions present. So when the reaction is over, we need a way to separate our desired product. One separation method is extraction, which is based on solubility. This video focuses on liquid-liquid extraction, which includes the use of two immiscible liquids to perform the extraction. As you know, molecules have different solubility in different solvents. For example, charged molecules are soluble in aqueous solvents, whereas organic molecules are usually soluble in organic solvents. However, depending on the functional groups present, we can make a compound to become soluble in water or soluble in an organic solvent. Let me explain what I mean by that. Let's look at hexanoic acid. It has a long hydrocarbon chain, making it insoluble in aqueous solvents. Now, what happens if we add a base such as sodium hydroxide? Well, remember carboxylic acids are strong acids, so an acid-base reaction happens resulting in a carboxylate anion. Now, this is going to be soluble in water because it is charged. So this is how extraction works. We take advantage of the functional groups to make molecules move to different solvents or phases to separate them. Let's go over a few examples. We have a mixture of aniline and nitrobenzene. Looking at the functional groups, aniline has a basic functional group while nitrobenzene doesn't. So if we add an acid, such as hydrogen chloride, to the reaction mixture, the amino group gets protonated and becomes charged, moving to the aqueous layer, while nitrobenzene remains in the organic layer. So in this case, we're taking advantage of aniline's unique feature, which is its basic amino group. Let's go over another example. In this reaction mixture, we have aminobenzoic acid and ethyl aminobenzoate. First, look at the structures and try to identify a unique feature for one of the molecules. Well, both molecules have an amino group, so we can't take advantage of that. Benzoic acid has a carboxylic group, which we know is an acidic group. Ethyl aminobenzoate, on the other hand, does not have an acidic group. So the unique feature here is the carboxylic group. How can we take advantage of that to separate these two molecules? Exactly. We can add a base such as sodium bicarbonate to deprotonate the carboxylic group and move it to the aqueous layer. Here's a question for you. What would happen if we add sodium hydroxide instead of sodium bicarbonate to this reaction mixture? Remember, hydroxide is a strong base and can hydrolyze esters, which we don't want to happen here. So this is why it is important to know what we have in the reaction mixture and take into account any side reactions that might occur when choosing the proper reagent to add. As a last example, let's look at a mixture of benzoic acid, phenol, and anthracene dissolved in ether. Anthracene doesn't have any functional group, so we're going to leave that alone for now. Phenol and benzoic acid both have acidic functional groups. However, we know carboxylic acids are stronger acids compared to phenols, which can get deprotonated using either a weak or a strong base. How about phenols? Can you use a weak base such as sodium bicarbonate to deprotonate them? No, because phenols are weakly acidic, so they can only be deprotonated using a strong base. So then, we can first use sodium bicarbonate, which is a weak base, to deprotonate the carboxylic acid only. Benzoic acid moves to the aqueous layer, while phenol and anthracene remain in the organic layer. In this way, we can separate benzoic acid. Next, we can use sodium hydroxide to move phenol to the aqueous layer and separate it, while anthracene remains in the organic layer. If we had used sodium hydroxide first, it would have deprotonated both the phenol and benzoic acid, which would not have been helpful to us. The glassware used for extraction is called a separatory funnel, which helps us to visualize the two aqueous and organic layers clearly. We add the reaction mixture in here, which is usually in an organic solvent. We then add the appropriate reagent depending on what we have in the mixture as discussed earlier, such as an acid or a base. Next, we shake the funnel a few times, making sure to vent the pressure so the glass is not shattered, and then let it sit for a few minutes. We can then clearly see two layers being separated. One is the aqueous layer and one is the organic layer. Water usually has a higher density compared to organic solvents, so it is usually the bottom layer. However, that is not always the case. If unsure, you can check by adding a few drops of water and see which layer grows. The layer that grows is the aqueous layer. We can then drain the bottom layer to separate it and continue with the extraction. Here are a few tips for a successful extraction. 1. Before pouring anything, make sure the stopcock is in closed position. Always have a flask underneath to catch liquid in case it was not closed. 2. Use a funnel to add mixture to the separatory funnel. 3. Make sure to vent the pressure when shaking the separatory funnel to avoid accidents. 4. Remove the stopper while waiting for the layers to separate and when you want to drain liquid. 5. Keep all the liquids until you have confirmed you have the desired compound. 6. If unsure which layer is which, just add a few drops of appropriate solvent to see which layer grows. Let's review quickly. The basic principle of liquid-liquid extraction is to take advantage of functional groups to move compounds to different solvents. Start by looking for a unique feature that might distinguish one compound from the rest. Consider other side reactions that may also occur when choosing which reagent to use. Thank you for watching.